All right, let's talk about waves. All right, so there's kind of two types of waves out there. There are mechanical waves, and there's also electromagnetic waves. This is for later. We are going to focus strictly on mechanical waves for now. Okay? So a mechanical wave is a traveling disturbance in a medium. Okay? So a mechanical wave requires a medium within which to travel. All right? Electromagnetic waves can travel through nothing. They can travel through a vacuum. But we're talking about the type of waves that you might find in a slinky or a string or even in water. Okay? So it's a traveling disturbance in a medium. And kind of a good definition of a wave is that it's a transfer of energy. So waves transfer energy from one place to another. Okay? Waves do not cause a net transfer of medium from one place to another. Okay, so waves in a mechanical medium, I mean, you require the medium in order to have waves to begin with. So when I say medium, I just mean anything the wave is traveling through. So this line right here will say represents a string or a spring. And what we'll do is we'll imagine that we put a wave into this. Okay? And we'll just do what's called a wave pulse first, which is just a deflection of the wave in one dimension. I don't like the look of that. It's not nice. There. Okay? So what I'm saying I did here is if my hand was down here, so I can draw a hand. Really? I don't know. So what I've done is I've given this a sharp upward jerk and then returned it back to its neutral position without going past. Okay, so I've just disturbed the medium on one side. Okay, so we might call something like this a wave pulse. Oops, pulse. Okay, this is the amplitude of the wave pulse. Amplitude. And this is wave displacement from neutral. Okay, so amplitude is always measured from the neutral position. Okay, we might actually have a wave pulse that looks like this. Okay, and now essentially what we have is we have kind of a continuous wave, or a wave train, some people call this, a wave train. But we would also consider this to be the amplitude in our wave train, right? So amplitude is either positive or negative from the neutral position. Sometimes people will want to say the amplitude is from the top to the bottom, but that is not correct. It's not from the top to the bottom. Okay? It's just this in here. Now this type of wave that I've drawn, okay, this is called a transverse wave. We'll just label that. Called a transverse wave. And you know a transverse wave because the medium is displaced transversely to the direction of travel, okay? So the wave would travel along this way. We call that its velocity, right? The speed or the rate at which it's traveling is called its velocity. And we know it's a transverse wave because the medium moves this way and this way while the wave moves that way, okay? So medium is displaced. I'm drawing the symbol for perpendicular to velocity. Okay, so that's a transverse wave. So just a little example here. We look, these dots move up and down, but the wave itself moves along like this. So the wave moves along to the right as the dots move up and down. Okay, so looking at this, you know, here is kind of what we're talking about. This, our waves move like that, but our particles move like that, okay? The next thing we need to kind of look at here is something called wavelength. So wavelength is the distance for one complete oscillation of the wave, all right? So when I say oscillation, I mean that that particle has gone up, down, down, and then returned to its initial position, okay? So we call that one complete oscillation. So the wave looks like this and has a bottom on it. Then one oscillation is a time to go up, down, and come back, okay? So that's going to happen from bottom to bottom or from top to top. We call these troughs, from trough to trough or crest to crest, or from neutral to neutral, all right? Because if you think about it, you know, a particle would have to go all the way up from here and then back down, and that would be considered one oscillation. And then the next time it happened, okay, we would come back to where we were. And there's a symbol for wavelength, actually. Why do those all look like little arrows? That is quite strange. So, okay. So the symbol for wavelength is that, and it is the the distance from crest to crest or trough to trough. I don't think I like this very much. It's weird. So to go from crest to crest or from trough to trough, that is one. Yeah, it seems like it wants to stick around. One oscillation. Okay, so the particle, as the wave comes by, starts here, it goes up, back down, down, and back up. Okay, so kind of like we're doing that. And the distance between one of those works out to be one wavelength. This symbol, by the way, is the Greek letter lambda. Look, it's over here. Oh, that's weird. The arrow starts where I started from. That's lambda. So lambda equals wavelength. So weird. Okay. So there's that. I think that explains more or less all we need to know about transverse waves for now. Let's quickly look at a longitudinal wave. So these are a bit harder to draw, but I'll try my best here. So imagine that the medium is a bunch of kind of connected dots here. And we have a wave pulse where we have a compression of the dots, followed by a spacing out of the dots, followed by just the normal medium again, okay? So in a longitudinal, this is like if you took a spring and you compressed it towards yourself and released it. Okay? That compression would travel along through the spring. So this represents the compression and the rarefaction. It would have a velocity in that direction. There's a compression and a rarefaction. I mean, that kind of makes sense. Like the word compression we use quite often. You're pressing something together. And rarefaction comes from the word, like, I guess, rare, where the particles are less compressed or you run into them more rarely. So we have that. This also has a wavelength, right? It's the distance from the start of a compression to the end of a rarefaction. It kind of has an amplitude. It would be like how much compression there is. We would consider that to be like the amplitude of the wave or the equivalent of amplitude. And I think really that's probably all we need to cover with that. Longitudinal waves are common, but they're not really that easy to see. So for instance, sound is a longitudinal wave. So it's a compression followed by rarefaction of molecules of air, okay? And then the next thing we need to talk about are frequency and period. Okay. So first thing we'll talk about is period. And this is the time it takes for one wavelength to pass. So one wavelength to pass. I probably won't bother writing wavelength anymore. I'll just use the lambda symbol. Okay. So I've inserted a GIF in here that shows a longitudinal wave moving along, just because there was some question about it. And basically, if we look, it's kind of clear that we can see the wave fronts moving along. Let's see here. Let's make it bigger so we can see the credit for the GIF goes to Dan Russell. It's a good GIF, well-made GIF. And so the fronts in the GIF are there. Well, there's one. And there's another. Okay, so if we start our clock, we 1, 2, 3, 4, we'd say this wave has a 4-second period. Okay, it's got a 4-second period. All right, so that's the period. Now the frequency. Frequency is how many waves per second we have coming along. How many waves okay? So if it takes 4 seconds for one wave to come by, how many waves come by every second? Well, it turns out that it is the inverse of period. So period has a symbol T, like in time, time for a wave. And the frequency then is going to be the inverse of it, because really, you have, it's not an I, it's just because my pen is putting arrows on everything, and I don't know why. So in other words, every second I'd only get a quarter of a wave, right? Like 1, 2, 3, 4, one wave, 1, 2, 3, 4, 2 waves, and so on. So the relationship between frequency and period is that one is just simply the inverse of the other. So in this case, my frequency is 1/4. It's a 1, but my pen is doing something weird with arrows, right? Just a 1. Yes. Because look, every time I write it, it puts an arrowhead on it. I don't know why. But irritating. Okay. Someone gave me a gift and showed me here that I had a little thing on there that, aha, there we go. No more arrows. Thank goodness. Okay. All right. So period is the time for a wave. Frequency is how many waves per second. Okay. And there is a unit for frequency. It's called the hertz. Hertz. So the frequency of this wave is 0.25 hertz, named after a scientist with the last name of Hertz who did a lot of work with waves. So hertz is, its unit then is per second, right? So this means anything happening per second. Now, in mechanical waves, you can have really slow waves. Probably not this slow, but really slow waves. If you get into light waves, you get into like megahertz or very, very high frequencies, okay? Because the waves are moving so fast.